Okay, so here we'll be revising the method of joints. And in this case, we have this question here. And in this question, they're asking us to determine the force in each member of the truss. And they also want us to state if the members are in tension or in compression. So depending on where we want to start from, it might be necessary for us to determine the reaction forces. If we're going to determine the reaction forces, then we'll first consider the whole structure and use sum of forces and sum of moments. But if we choose not to determine the reaction forces, we can start from the top and then break it down. But if at any point we feel like we need the reaction forces, we can still come back and determine them. So to sort out, yeah?
Huh?
You're saying? Okay. So which approach would you want us to take here? Would you want us to figure out the reaction forces in advance, or we can start from anywhere, and should we need them, then determine them? Okay. So if we're going to determine the reaction forces in advance, then we want to draw a free body diagram of the whole structure. In this case, the internal forces inside the members are going to behave as they won't show up in the free body diagram. Only the external forces will show up. This being a rocker here, we know to say it only presents one reaction force, one reaction. And then we have this side where we have a pin. A pin will present two reaction forces. So if we are to do that, so where we have that rocker at point A, we have one reaction, let's label that as AY. And then at E, so we've labeled that as AY. And then at E, that being a pin, we can assume the reaction forces. We have one going up. We can label that as EY. And then we can have one in the x-axis. And we can assume it is going to the left. And you can label this as EX. Then for that structure, so for you can actually just redraw that structure. And when you're redrawing it, you don't have to draw every single detail. You can actually just draw the outline. You can have this, you can have this, you can have that, then you can have this. Once you have that, then show the forces, this, that one there, and this one there. So having done this, of course, you can also show those reaction forces. So overall, your free body diagram will now look like this. So your free body diagram can look like this. Then the only other thing that you can indicate here will be the length, since you need them in the evaluation of moments. So this is in an event where you have to redraw this. You don't have to show those minor details inside. Okay, so with that out of the way, how do you evaluate this? Well, there are two methods that are at your disposal here. You have sum of forces equals to 0 because the whole system is in equilibrium. And then you also have sum of moments equals to 0. So we started sum of forces, and we'll do it first in the x-axis. In the x-axis, how many forces can you see there? 3. So taking to the right as positive, the 2 kip is to the right acting at H. And then we have the 1.5 kip is also to the right acting at I, EX being the only one going to the left. So we have 2 plus 1.5. The only one to the left is EX. This has to sum up to 0. So in the end, we have EX is equals to 3.5. So we have found what EX is. When we sum forces in the Y now and also equate to 0, we see that we have 4 forces in the vertical. So we have AX, AY, AY, and the force at G and that at F. So taking up as positive, we see that we have AY, plus EY minus 3 minus 3 is equals to 0. So this is what we have here. So that AY plus EY is equals to 6. From here, we see that we need at least to know either AY or EY to find the other. Now, what method are we going to use to find one of the reaction forces, one of the vertical reaction forces? Moments. So we can take moments about a point. So which point is going to be suitable here? Yeah. So we're going to evaluate moments at point E. Point A can work as well, but we can use point E here. So if we take moments about E, then EY and EX will not cause a moment. So only AY and the other blue forces there will be causing moments about E. So now we're summing moments about E. So if we do it about E, force times distance, perpendicular force and distance, we see that the moment due to AY about E, will it be clockwise or anti-clockwise? What do you think there? AY about E, is it causing a clockwise or anti-clockwise moment?
Clockwise.
Clockwise, yes. So AY will be causing a clockwise moment. It will be trying to rotate the structure in that manner. That will be clockwise. So it will be minus AY multiplying the distance, which is 10 plus 10, 20, 30, 40. So this becomes 40 AY. Then next, let's look at the others. So when we check for the other forces, we've sorted out AY. We now want to see what the other four are doing. So let's sort out the vertical ones. First, we can go to the one at G. The one at G is acting in the vertical direction like this. This time it is causing anti-clockwise, so we'll take it as positive. The force is 3. What distance are we going to use here? 20. So being anti-clockwise, it is going to remain positive. Then the 3 keep there. The one at F is also clockwise, anti-clockwise, I mean. So it will also be positive, it will be 3, but this time it will multiply 10. So that sorts out the two vertical blue. We then move on to look at the horizontal one. So for the horizontal one, we start at the 1.5 acting at I. We see that for this one, it is in this manner. The distance from the point E to that line, the line of action, will have to be a vertical distance. And in this case, when you look at this part, that distance is given as 4 feet. So it's going to be, and when you look at it to be causing clockwise, so it will be negative. So it will be negative 1.5 and it will multiply 4. Then the other will also be causing clockwise about E. The distance will have to be 4 plus 8, which is 12. Being clockwise to be negative as well. The force is 2, distance is 12. So this now sorts out all the forces and their respective moments. So our equation becomes this. But this has to be equals to 0. So all we have to do now is simplify this expression and make AY subject. So I'll take AY to the right-hand side, shift it around, and make it subject. So we're going to have 3 by that is 60 plus 30 minus, this is going to be 6 minus 24 over 40. What will be the solution here? I hope you saw it's the 40 AY that went to the right, becoming positive. All the other terms remained to the left. I just rearranged after. Over 60 over what? Over 40. Divide 1.5. So we have determined the reaction AY. And when we go back to our equation 1, AY plus EY was equals to AY plus EY was equals to 6. So this implies that EY is equals to 6 minus 1.5. EY will be equals to 4.5. So we now have all the reactions. We can now move on to solve our problem. Knowing the reaction forces gives us a little bit of freedom here. How do we work out this problem? Well, up to us. We now want to pick a starting point. We know the reaction force at A and also at E. So I've got freedom to start at this point, start at that point, and to start at that point. Those are the three best starting points that you have. The idea here is your starting point must have at least, at most, it must have 2 unknowns, not 3, just 2 in this case. So you want to avoid points like G, because at G there, you will have too many unknowns. This will be an unknown, this will be an unknown, unknown, and unknown. F will be the same as well. All these will not be known. But when you look at a point like H, for the point H, you will have a given force here, and the only unknowns will be the 2 members there. So we can work with H. Having determined the reaction forces implies that we can work with A as well. Because for A, we'll have this unknown, that unknown, and the reaction at A as the only known force. So it implies that that can work as well, including E. For E, 1 unknown, the second unknown, and the reaction forces have been determined. So in this case, we're saying that even E is a good starting point. Which point do you want us to start with here? Point A. Did you say A? Yes, okay. One key thing that you want to just keep in mind when it comes to the method of joints is that what we are looking at here are the forces acting on the joint, not necessarily what is happening inside the member, but we use what is happening to the joint to predict what is actually happening inside the member. For example, if you have a member like this one, and let's say the member is in tension, it implies that the being of that member, let's say the molecules of that member, are being stretched apart. So the molecules are being stretched apart. Then we're saying that the member is in tension. So in this case, this describes the internal forces of inside that member. So in this case, we say the member is in tension. But if the member was being compressed, meaning pushed inwards, now in this case, the molecules inside the member will feel a force trying to close them in together. So this is what we'll be seeing the molecules, or this is what the molecules will be experiencing. In this case, the member will be said to be in compression. But when we're evaluating the method or using the method of joints, we're not necessarily looking at directly what is happening inside the member. Instead, we are looking at what the member now is doing to the joints. So this is what we are looking at. A good example that you can take here is for a spring. So if you have a spring, and then let's say the spring is in its rest position when it is in this state. And then I stretch the spring. so that it goes up to that much. So let's say this is our stretched spring. So we stretch the spring in this manner. Now, since the spring has been stretched, in what state is it? Compressive or tensile? Tensile. Tensile. So this is in tension. But if I was now to give the spring to you while it is still stretched, and then ask you to hold it from both ends, hold it there and hold it here. Notice that in this case, your hands are behaving as the joints here. What will the spring be doing to your hands? Yes. The spring will be pulling your hands towards each other in this manner or inwards. What is the point here? When a spring or when our member is in tension, the force it exerts on the joint is an inward. So it acts away from the joint. So if you have a member that is exerting a force on a joint such that the joint is being pulled away from that, or they say the force is acting away from the joint, then we conclude that that member is in tension. And if you had the opposite, a joint is here, and this joint experiences a force from the spring that is acting towards the joint. In this case, we're going to conclude that the member is in compression. Again, you can still use the logic of the spring to see what the spring will be doing to the joints. If you had a compressed spring and then you're trying to keep it compressed, the spring will be pushing your hands outwards. So you get compression and tension when it comes to the method of joints, right? Okay, now let's pick point A. Now, when it comes to this method, you really don't know whether the joints are in tension or compression. You might be able to predict when you look at the system very well, but no need to stress too hard. All you want to do is, for the forces which are well known, like the reactions at A, we saw to say the reaction at AY will be going vertically upwards. So start with those. Get rid of them first. So the reaction at A will be acting upwards at A. So this is AY. Now, after that, you have two members. Now, for the members, you just have to assume. All you know is that either the force in each member will be acting towards the joint or away from the joint. So in this case, I will always assume that the members are exerting a force that is outward from the joint in that direction. Meaning that for the horizontal one, my assumption is that the member is exerting a force that is horizontal and pulling to the right, pulling our joint to the right. When it comes to labels, since this is running from A to I, I'll label this one as FAI, and the other one, I'll label it as AB. So this will be AI, and I'll label this one as AB. Now, assigning the two forces in this manner, what am I assuming? Am I assuming they are in tension or they are in compression? Tension. Yeah. So again, away from the joint implies tension. So when in our calculation, we find that any of these forces in red comes out to be negative, it will imply that the actual state of that member is actually compression, not our assumed tension. So all we have to do now is some forces. The idea here being that if the whole structure is in equilibrium, then even the respective joints must also be in equilibrium. So let's do some quick math here. The AY is already in the vertical. We know FAI will have two components. One is going to be horizontal, one is going to be vertical. So let's start by summing forces. In the x equates to 0, we need to express AI in component form. To do that, let's go back to the diagram and look at if we can find an angle. Well, we know from here to here, it's a 10. And from here, B to I, that is a 4. Implying that we can easily write this as a triangle and find the angle which is there using the two sides. Or you can use ratios, but old school. So I prefer just going with the angle there. So this is 10, and that is 4. I can assign this to be theta and say that theta will be tan inverse of opposite over adjacent. So what will be our theta there? $71. 21.8 degrees. Okay, so given the angle there, it implies that we can now break down or represent FAI in parts. Say 20 what? 21.8. Okay, so summing forces in the X, FAB is to the right, so positive. Then we have plus the X component of FAI. This will be FAI. Then this will be cos that 21.8. There will be the only two in the X at that joint, so we equate to 0. So this will just tell us that FAB is equal to negative FAI cos 21.8. Then when we sum in the y-axis, in this case, we see that we have AY going up. Then also going up, we've got the y component of FAI. So this will be plus, but this will be sine 21.8. They are the only two, so equals to 0. So when we make AY subject, this will be negative. This becomes the third. From here, we can now combine these two equations. So, did we leave anything here? Well, we did not. But we do know what AY is, right? What was our AY? Let's go up. AY is 1.5. So equation 2 can actually be simplified further. Since AY is 1.5, we can put 1.5 here, then minus FAI sine 21.8. So this implies that FAI is equal to negative 1.5 divided by sine 21.8. What will be the answer here?
And 4.04.
4.04. Now, this force came as negative. What does that mean? Yes. But don't really take it that our assumption was wrong or something. It feels like we were wrong or something. But it just tells us that the member is actually not tension, but it is compression. You've got that, huh?
Yeah.
So this sorts out FAI. We now do the same thing for FAB, but having written equation 2, we'll just get this. Where we have AI, we'll just substitute. But which version of AI are we going to put here? The positive one or the negative one?
The negative one.
The negative one. We came up with these equations with the negative one, so you have to keep going with them. So this is going to be negative 4.04. Then we have cos 21.8. The answer here will be what? 3.75. So this comes out like this, implying that our assumption stands. This member is in tension. Any questions there? Okay. So this sorts out those two, but the journey continues. Having figured out this and this, we can now come here. Now, what you see here is that this starting point was not really a good starting point, because after sorting out B, we will know what this is and what this is. But look at the next points that are showing up. This point, for example, will have this as an unknown, this as an unknown, and this as an unknown. So it will mean that it will be a little bit hard for us to evaluate that one. And when we come to this one also, it will mean that even though we'll know BC, we'll not know CI, CG, CF, and CD. So we're going to find that complication there. Have you seen that? So don't worry with that still. Once we reach point B, we can pause our approach from here and quickly switch to the other two. We identified 3 possible starting points. This one led us into a little bit of a mess, but we can quickly switch to either E or H so that we now approach those complications from the other side. In fact, H is going to pose a good starting point, because once we get, not necessarily, not the best really, but when we come from H, it was going to give us this one and this one, meaning that now for point I, would have known this one as well, meaning that only 2 unknowns will remain. Do you see that? Okay. So let's move towards point B. But can you make any observation about the members acting at B here? Can you make any quick observation before we even start?
What's the color change like?
Zero force members. Yeah.
Zero force member, that one, the straight one.
BI. Yes. In this case, we expect BI to be a zero force member. Can you observe this structure and identify another zero force member here?
DF.
D what? DF, right? Okay.
Yeah.
So you just want to keep that in mind. If you're rushing against time, you can quickly just say this is 0 and then proceed. But if you've got enough time to spare, you can still show some calculations there so that you're just sure. Okay. Especially maybe for DF. But when you know to say it's a zero force member, you can just glide through it. Okay. So let's go to joint B. So when you look at the joint at B, what do we have there? Well, joint B is easy, because if this is the joint, we already saw that, where's that AB? AB came out as what? Positive or negative? It was positive, right? We found AB as, no, AB came out negative, right? No, it was positive. AB was positive. So meaning AB is guaranteed and verified to be pointing to the left. Next up, we have another force the other side. I will assume the other force will point in this direction. And lastly, I'll assume this force to be going upwards. But what are the labels for these other 2 forces? So let's check them out. We have BI and BC.
Question.
Go ahead.
If for every point, I assume the forces are going outside. continue. That when they're asked it, how does it do for every point?
For every point.
Instead of changing.
Like the way I've done the point B.
The way you do for it, yeah, exactly.
This is fine.
For every point, right? You don't
Yeah,
change
yeah. For every point, I'll keep doing this, but wherever I find a negative, it will mean the opposite. I should write the answer as compression.
But when solving, I can still take every point as this. Like I don't have to change.
No. Once an assumption has been made, you don't have to come and change.
Okay.
You get that, huh? Okay, so let me check the labels again. We have BC and BI. Okay, so when we sum forces in the X, we see that in the X, we have BC to the right. Then we have FAB to the left. They are the only two, so equals to 0. This implies that BC is equal to AB. But we do know AB. We just found it. AB is 3.75 kip. This implies that even BC is 3.75 kip. So BC was straightforward. And we conclude its orientation is fine, it is in tension. Now, when we go to sum of forces in the Y, for this one, it's actually very straightforward because we observe that only one force is in the Y-axis, which is FBI. So we only have one force, FBI. So on its own, it has to be equals to 0. And for this one, there is even no angle. So we just get that. So our observation or our prediction that it was a zero force member stands. So like I mentioned, having sorted out point B, continuation has proved to be a little bit tricky for the joints that are up next. So we're going to pause our approach from this side, having sorted out this, and those other two. Now we're going to approach using the other sides. So we'll now move to point the joint at H here. So for the joint at H, what is happening? So if this is joint at H, the 2 kip is already given and it is going towards the joint. We can't change this. But for the other members, we can now make our assumption. We'll assume we have a force running from H to I, putting HI as tension. Then we'll also assume we have HG, setting HG as tension. So we have F, HI, and then we have F, HG. So this is what we have here. Now, of course, we see that HG will need to be resolved. So how are we going to resolve it? How would you do it? We need to resolve HG, meaning we need an angle or sides. How would you do it? Use the vertices. What would be the letters to show the vertices of your triangle?
HI.
HI.
But that's even there.
Yeah, we can. HI. What else?
And with that other side, this name that's down there, this is use that.
From where to where? Use letters then.
DC.
DC.
The left there. B.
BC.
That is that length there down.
Yeah.
Then we've got that length from H to I.
So we've got H to I. And which one from here? BC.
Yeah.
This is not a triangle.
Yeah. Can use half of.
No, but look, notice that BC is a triangle. And it would help us to get this angle. Do you see that? The most obvious one that I expected you to see was from H all the way to B, then all the way to E, then all the way to H. You see that? It also helps us to get this angle there. And that angle will be this one here. Do you see that? So that angle will be given by tan inverse. And the sides, the opposite will be from B to E, which is 30. The adjacent will be from H to B, which is 12. What will be the angle?
Uh,
58.20? 68? Okay. So now that we know theta, we can easily sum forces here. Okay, so this is at H. So let's see, in the x-axis, we've got the 2 going to the right. And then we also have FHG. This is going to be sine or cos.
just again. SHD.
FGH, will it be sine or cos? I'm getting the x component. Okay. Nice.
You mean X?
You already got it right. Don't try to get it wrong. Yes, I did. Okay, so x will be given by sine. So this will be sine that angle, 68.2. There will be the only 2, so this will be equals to 0. This will imply that our FHG will be equal to -2 over sine 68.2. What will be the answer here?
-2.15.
-2.15. So what is our conclusion? Yeah. Okay, so this is what we get there. Having found FHG, we can now sum forces in the vertical, and let's see what we get there. Is equals to 0. We have our FHI going down. FHI going down. Then we've got the Y component of HG. The Y component of HG will also be going down. So you have minus FHG. This one will be given by cos 68.2 is equals to 0. So in this case, we're going to have FHI being equals to negative FHG. Then we have cos 68.2. We substitute what FHG is. So we found 2.15 negative, don't forget. Then we have cos 68.2. So that in this case, our answer becomes this, cos 68.2. What will be our answer? Pardon? You want to recalculate the first one? 0.80. Can you give it to me in 236? 0.79. 0.798, like this? Yeah. So this is intention. So we have now found FHI. So notice that using these joints, we have already sorted out these members. We have sorted out AB, we have sorted out AI, we've sorted out BC, we've just sorted out HI, and we have sorted out HG there. Our next point will now come back to point I. And for point I, when we draw that, this would have, so this would have, let's assign the forces. So notice that in this case, we already know the state of HI. Do you get that, huh? So since we already know the state of HI, it's up to you. If you decide to continue using that it is in tension, even though that you know that this maybe is not in tension. Let's see, what did you have for HI, for example? Let me also write IA or AI. Let's say I still maintain that this is tension like this. What would this imply? Well, in this case, for example, AI, we found AI, and AI was compression. So if I choose to use that orientation, which is predicting AI as tension, then I must use the negative version of AI. Do you get that? Yeah. So which method would you want us to use? Where we know the orientation, should we use the correct orientation, or we still keep working with tension? Okay. So once you choose that approach, be very careful to not forget the negatives where they have to be included. Okay, so that is what we have there. And BI, we saw that BI was a zero force member. We wanted to write it like this, but because it is a zero force member, we can actually ignore it because it won't really do anything. Next up, we have IG. IG, in this case, goes something like this. So this is FIG. And lastly, we have IC. IC comes like this. FIC. So just as we did for the others, we can actually work out these. We will only have two unknowns, two equations as well. So it will be easy for us to sum. Hello? Okay. So in the same way that we're able to get the other members, you can now sum forces for this structure in the X, come up with one equation that will have IG and IC as the only two unknowns, and then sum forces in the Y-axis as well. Then solve the two equations simultaneously. you're going to figure out what this one is and what this one is. Once you know these two, you can move to G, point G. And using point G, you can figure out what this is, and then come to C. Since you now know this, this, and that, figure out this one and this one as well. Then see that as you go on, everything is coming out. Come to D, figure out this. You already know this, so figure out this one and this one. And then come to F, figure out this. Then you're done with all the forces in that structure. So if you wanted to find a way of resolving this force here along that member, what you have to see there is that what you have is a straight line running from A through I all the way up to G. Then you have a horizontal line from A going all the way up to D. Now, you have to just keep in mind one thing. The force through I, as in from I to G, is running in this direction, in this way. So if you wanted an angle to break it down, notice that what you're trying to achieve, what you're trying to find, is a component of this force in this direction and a component in that direction. In other words, you are looking for this angle here. But can you see that this angle here is actually going to be the same as this angle here? Since this line and the x-axis there are going to be parallel to each other. And this angle here can easily be found. I think we found this angle. When we just started, we did find it. We found this angle here. So use the same value here. It's the one that will go there. So this is how you're going to resolve that force there. In the same way, you can try to see